I'm the publisher for these journals, and it's my pleasure to welcome our editors-in-chief of JWPE, Xiaocheng Wang, and Ludo Dumi, as well as the editor-in-chief of Desalination, Professor Sean. And Ludo will give an introduction of the journal and introduce our speakers for today. So Ludo, over to you, please.
Thank you very much, Luane. And thank you all for joining for our
recording in progress.
2025 webinars. Today, we are very lucky to be able to congratulate first GWPE 3-minute thesis competition that took place in October-November 2024. And the top 3 winners will actually present their work to us today. Before we do so, we have a brief introduction on the webinars and on some of the outreach programs that we have developed jointly with Desalination and the Journal of Water Process Engineering in the last 18 months or so. So first, on Desalination, obviously, Professor Tao He and Professor Hanwei Yu are the 2 editors-in-chief. Desalination is focused primarily on the application of publications related to papers on desalination and water treatment at large. It's one of the most prestigious journals in the water area, and you can see an impact factor in 2023 of 8.3 and very low, therefore competitive acceptance rates of around 29%. Desalination obviously doesn't completely overlap with what we do in GWPE, where we try to focus more on the water process engineering aspects and also water treatment without doing publishing materials on desalination technologies. In our case, we have been trying to develop for the last 18 months a number of outreach opportunities for students and also mid-career researchers. So we launched in 2024 the free MT competition and also a Trailblazer Award, and I think we'll be able to announce the winners officially in the next 2 to 3 months once their publications are through. We have been present and we welcome you obviously on the social media with LinkedIn, WeChat and Twitter, where we try to promote activities and hot papers. Both Desalination and GWPE have the same approach there. And we're going to have more joint events in 2025 as we move forward in the new year. Now, this is just a snapshot of the last 18 months, give or take, or nearly 2 years now, actually, of the webinars and the speakers we have had. So you can see we have been very lucky and privileged to have a number of top speakers. Some were editors, but the majority are actually not. They were researchers, people who have published in Desalination or GWPE, or obviously, for the talk in December, the founding editor in November of both Desalination and of GWPE, so Mayam Balaban and Nick Hankins. I will stop here because I think we have a busy schedule with the 3 speakers. I don't want to take too much time, but thank you once again for joining, and we look forward to our speakers. So now I may ask our first speaker, Hanwei, to please share her screen. So Hanwei is a PhD student at the University of Technology, Sydney in Australia. In fact, also working under Professor Hanwei Yu. So I think, Hanwei, the floor is yours. And please, if you have any questions, you are welcome to put them into the chat. We'll go through the 3 speakers before we have the question time. Okay, so you can just in the comments highlight which speaker your question is for, so that we can actually follow up at the end of the session. Thank you. Hanwei, if you can go full screen, please. Yeah, you have to change the presentation. You are in the presenter mode right now, please.
Oh.
Yeah, perfect. Thank you. Floor is yours.
Sorry, my laptop has some problem.
You okay?
Sorry, my laptop is stuck here.
Okay. Can you
Okay, I think it works now. Yeah. Sorry.
Just try to change one slide. Make sure it's right. Try to change one slide, please, because for me it's not changing on the screen.
Can you see?
Okay, it's working. Yeah, we can see. Okay, thank you. Thank you so much. Floor is yours. Please go ahead.
Okay, good morning, good afternoon, and good evening, everyone. My name is Hanwei Yu. I'm a PhD student from UTS under supervision of Professor Hokkien Sheng. And thank JWPE for providing a platform allowing me to present my PhD research, which is about selective lithium recovery from seawater brines using capacitive deionization. First, to start, let's have a look at the growing importance of lithium in today's global market. Lithium is a critical resource primarily driven by its role in the battery industry, which now accounts for the 87% of global end-use consumption. Beyond batteries, small but significant applications include ceramics and glasses, lubricating greases, air treatment, medical uses, and mold flag powders. The demand of lithium in the past decade has grown dramatically, fueled largely by the rapid development of the renewable energy technologies and electric vehicles. According to the latest statistic data from the USGS, the global lithium consumption reached 180 kilotons in 2023, representing a remarkable 27% increase compared to 2022. But if we compare this to 2010, when global consumption was just 25.9 kilotons, it's an almost sevenfold increase in just over a decade. This growth underscores the critical roles of lithium in the supporting sustainable energy transitions and highlights the urgent need for exploring more lithium resources and more efficient lithium recovery technologies. So now let's discuss the distribution of lithium resources and the method how we extract lithium. Lithium resources on land are finite and unevenly distributed. Hard rock mining, which is one of the primary extraction methods and what we are still rely on, has several significant drawbacks, such as it is non-renewable, it's chemical and carbon intensive, and most importantly, the lithium ores are very limited. In fact, the lithium reserves in ores only account 1/4 of all lithium found on land. And a larger share of lithium is found on land brines, such as Salt Lake and geothermal brines, where the reserves are about 3 times higher than those in ores. However, the truly untapped potential lithium resource is in the ocean. Over 99.9% of lithium is stored in seawater. It is over 10,000 times more than the total reserve on land. But extract lithium from the seawater-based resources is very challenging. What happened?
Yeah, I think you left the full screen.
Oh, okay. Can see it now.
It's good.
Oh yeah. So it's very challenging to extract lithium from seawater-based resources, because there are the lithium concentration in seawater and seawater brines are very low, and more important, there are a lot of competing ions such as sodium, potassium, magnesium, and calcium. So the conventional approach to extract the lithium from aqueous resources include evaporation, precipitation, solvent extraction, and absorption. In recent decades, there are some emerging approaches to improve the selective lithium extraction, which are electrochemical method and memory-based method. And for my PhD research is a combination of the electrochemical method and memory-based method. I use CDI, it's called capacitive deionization, and membrane. So now let's take a close look at CDI. CDI is a novel and environmental-friendly technology originally developed for dissemination. CDI operates based on the electroabsorption processes, make it a highly promising next-generation solution for ion removal, energy harvesting, water purification, and resource recovery. CDI offers several advantages. It is technological simple, cost effective, operates under very gentle conditions, and requires low energy input. It typically runs under very low voltage, usually under 1.5 volts. Here is how it works. A CDI system contains a pair of electrodes. When a low voltage is applied, the electric field will direct the cation and anion towards the oppositely charged electrode. The electrode can temporarily absorb ions, just like a sponge soaking up water. Then, with a reversed charge, it can release this ion back into the desorption solution. So, building on the foundation of CDI, I'd like to introduce the memory capacitive deionization, or say MCDI. MCDI combines CDI with the membranes, usually ion exchange membranes or ion selective membranes, to enhance the CDI performance. The incorporation of the membrane brings several key advantages over traditional CDI. It can choose the pore size distribution of an electrode. It can adjust the chemical contact with target ions, and it can change ion selectivity. So my PhD research on MCDI cathode, it follows three directions to improve the lithium selectivity when recovering the lithium from aqueous resources. The first one is I use a morph-based material membrane on the activated carbon based on the size sieving effect. I use ZIF-8 based membrane onto a commercial activated carbon electrode. ZIF-8 is a promising ion separation material. It's well known for its substantial surface area and the sub-nanoscale pores. It is widely believed that it can achieve ion separation through a size sieving effect. ZIF-8 typically have the nanoscale pores, pore windows, and then nanoscale pore cavities. It looks like the photo shows, and when the competing ions and lithium comes through, the size sequence goes like the dehydrated ion diameter are smaller than if its window size. It can quickly pass through. And this is the ion transport process through the ZIF-8 membrane. As this when these cations attempt to enter these tiny windows, they undergo the partial dehydration. Once inside the large cavities, they rehydrate again. However, when they try to exit the cavities on the other side towards the activated carbon, they need to dehydrate again. So due to the variation in cations, dehydration in surface, they pass through the ZIF-8 membrane at different speeds, achieving the ion separation. So we we used the in situ growth method to simply grow ZF8 on the active carbon electrode, the result shows that the presence of the ZF8 coating substantially improved the lithium selectivity over monovalent ions compared to the original electrode. But it has a problem that, which is the poor hydrostability. To solve this problem, we further used the polydopamine to modify ZF8 and coat it on ZF8 polydopamine on the activated carbon electrode through the deposition coating method. And the SEM and the axiotic characterization results both confirm the greater improvement of the water stability. So after the ZF8 coating, we run the MCDI experiment under the same condition as the previous test, and the results shows that lithium removal rate and the lithium selectivity increased in monovalent cases after coating, and the presence of the ZF8 polydopamine built up the presence of the electrode to divalent cations. We also conducted the MCDI test under different voltage, and we evaluated the MCDI performances in terms of the metrics of the lithium selectivity, lithium absorption capacity, charge efficiency, and energy normalized to lithium. And we found that the applied voltage demonstrates negative relationships with lithium selectivity, charge efficiency, and energy normalized to lithium. And lithium selectivity in lithium sodium and lithium potassium feeds achieved 1.5 and 1.85 under 0.5 watts, confirming the potential to selectively extract lithium from seawater and seawater brine with a very low energy input. And the second direction we are trying to investigate is by using the functional group modified MCDI. The mechanism of this strategy is that many functional groups with negative charge that can have particular affinity to some cations. And then this study is regarding investigation of the feasibility to use sulfonated polyacetone membrane modified MCDI for lithium recovery. We fabricated 3 different electrodes by coating the SPK membranes on active carbon electrode using a casting knife, featuring by different sulfonation degree, namely is the SPK 20, 40, and 60. And here are the MCDI experiment results. We found that after SPK coating, the lithium removal rate and the lithium selectivity in lithium potassium feeds improved up to almost 280% and 150%. And the SPK membrane demonstrated a preferable affinity for capturing and releasing divalent ions. And the impact of the sulfonation degree was limited in monovalent cation competing cases, but noticeable in divalent cases. And now this is our third strategy based on the lithium ion safe adsorbents. Lithium ion adsorbents, including the LMO and LTO, which has the memory effect, that it has some specific sites for lithium. After activation, these sites are empty, exchanged with the hydrogen, and during the absorption process, the lithium ions is preferred to occupy these old sites first, so that increase lithium selectivity dramatically. And in this research, we use the LTO, EM, CDI for selective lithium recovery. Different from the previous two strategy. In this one, we directly use the simulated seawater brine to test the MCDI performance based on the literature data. And we test both under neutral and alkaline condition. This is how we synthesize and fabricate the LTO powder and LTO electrode. We use a calcination method to generate lithium absorbent, and using deep coating method to fabricate the cathode directly on the graphite sheet. Here is the absorbent and the cathode characterization results. The exotic characterization confirms the successful synthesis of the high crystal LTO, and it is from the SEM, so we can see that the LTO electrode is porous. And during MCDI process, initially we applied -1 voltage on the cathode and allowed the feed solution to pass through, and it takes around 20 minutes. And after that, we have the rinsing stage using milk water to rinse out the temporarily on the surface the competing ions. And finally, we're using milk water for the desorption. For evaluate the performance of this MCDI process, we have the metrics of the lithium absorption rate and the gross lithium selectivity and the final lithium selectivity. And for the MCDI performance, we found the result shows that around 60% of lithium in the feed solution was absorbed by the MCDI system. The pH has minimal impact on lithium selectivity. The gross lithium selectivity over competing cations are ranged between 10 to 20. However, with the rinse stage and the final active selectivity increased dramatically to over 200 during the rinsing stage. And here is we also did a 10 cycle stability test. We see the current density, pH, and conductivity was monitored during this 10 cycle, and these factors demonstrate a good stability over the test period. And the order of the gross lithium selectivity follows from the lithium magnesium over lithium sodium over lithium calcium over lithium potassium. But the active lithium selectivity order was lithium calcium, lithium magnesium, lithium sodium, finally lithium potassium. Overall, the selectivity values remain very high over the 10 cycles, all exceeding a factor of 100. Here is the conclusion. In my PhD research, I used the 3 strategies of CDI cathode, including the cooperating MOF, the functionalized membrane, and the lithium-ion sieves for CDI to extract lithium from the diluted lithium brines. And 4 electrode fabrication method was used, which are in situ growth, deposition coating, cutting knife, and deep coating. And the incorporation of the FIT and the SPK membrane shows the distinctive improvement in selectivity towards lithium in the presence of the competing ions. But the best one is still the lithium ion sieves LTO. The LTO EMC CDI system achieved the super high lithium selectivity, and it maintained active selectivity factor over 100 during the 10-cycle stability test. Finally, the MCDI performance also varied from the competing ions and apply the charge potentials. These are mainly my PhD research and my findings. Thank you, everybody, for listening to my presentation.
Thank you very much, Hanwei, for your presentation. And again, congratulations for being the winner of the 3MT competition that we organized last year. As I mentioned before, and I think, Luane, thank you, put a message in the chat. Please put down, I have questions for you, Hanwei, but I will keep them for later. Please put your questions in the chat, and we will go through the questions for the three speakers as a mini workshop at the end of the session. Okay.